In this screencast, we're going to go through the primary differences between nuclear fission and nuclear fusion, talking about some of the reactions that are very useful to us, some of the nuclear reactions that are useful to us. So when we think about nuclear reactions, a lot of times people think about nuclear power, and our energy production E equals mc squared, where E is the amount of energy that we can make, M stands for mass, and then C is the speed of light. So remember, we've got particles that have mass, and then we have like gamma rays that are just light energy. So we can use all of this to determine how much energy we can make. This is a very simple kind of nuclear fission reaction. I know it doesn't look very simple, but it really is. All you do is bombard neutrons to uranium-235. So when you take uranium-235, bombard it with neutrons, it causes it to form uranium-236, which is unstable. And then that leads to this nuclear decay. And when it decays, it gives off krypton-92, barium-141, 3 neutrons plus energy. That energy is what we use in nuclear power. It's used to heat water to then create steam. That steam turns a turbine, which turns a generator and produces electricity. So the key is, though, you release these 3 neutrons. These 3 neutrons can then bombard more uranium-235, and you end up with a chain reaction happening. So fission is splitting. That's by definition what the word means. A heavy nuclear particle is split into smaller nuclei by something even smaller, like a neutron. So the neutron hits it, causes it to split into 2 things even smaller, gives off some neutrons and some energy. It is accompanied by a large amount of energy, and it is self-perpetuating because you give off neutrons in that reaction. Those neutrons then go back and bombard more to make it keep going. It can be used to generate steam, as I had already said. So nuclear fission is when scientists bombard a large isotope with a neutron. It causes the large isotope to break apart, and during the process releases a lot of energy, 10,000 times more than just a regular chemical reaction. So it's actually very efficient because you get a whole bunch of energy coming off of it. We think of nuclear fission when it's controlled. When the reaction is controlled, those neutrons are kind of kept in check. That's how we make nuclear power. If you let it go and there is no control mechanism on it, so uncontrolled, that's when you have an atomic bomb. So here's what I was talking about in diagram form. So you take a neutron and you bombard it with uranium-235. That then splits into krypton, barium, and 3 more little neutrons. Those 3, and then the energy is released. Those 3 more neutrons, or 3 neutrons made, can then hit more uranium-235, and you get even more barium and krypton and more energy released and even more neutrons. So the reaction just keeps going once it starts. We call it a chain reaction. So kind of the basics of a nuclear power plant, how one works. You notice there's really 2 parts to it. There's the part that has the nuclear side of it, and then there's the part that's generating the electricity. So in the nuclear side of it, you have your reactor core. This is where those neutrons are hitting these fuel rods in here. And the neutrons are causing a lot of energy to be released. Well, that heat energy is trapped in these pipes, and it makes water boil. Well, that heat energy is then just cycled through, and you just have this kind of closed off system where all this radioactive energy is staying in. So the water is heated up, produces steam. That steam then turns a turbine, which then turns a generator, which will produce electricity. Once the steam is done turning the turbine, it condenses back down, and that water it's then condensed back down using colder water, and that water is kept in this system. So you notice this water never leaves this system. There is water that is pumped in from the outside, and that's why there's like a lake usually by all nuclear power plants. Even Wolf Creek has one. And this water is what's not going to come in contact with anything radioactive. It's just cold water that's used to condense the steam back so it can be reused over and over and over again. So that's how the nuclear power plant works. Nuclear fission, in 1 kilogram of uranium, you can make the same amount of energy that 12,000 liters of mineral oil and 19,000 kilograms of hard coal can. So way more efficient. than coal-fired power plants or using oil for energy. So a little bit more about nuclear power plants. In the U.S., there are approximately 100 nuclear reactors, make about 20% of the country's energy or electricity. The advantages, there's no fossil fuels that are burned, so you get no combustion products. There's no acid rain. There's no carbon dioxide or greenhouse gases put into the atmosphere. The disadvantages, though, they are expensive to build and operate. Obviously, there's a great deal of security with them. We do have a limited supply of fissionable uranium-235. And we really don't quite know how to dispose of the rods, the uranium-235 rods, when we're done with them. It takes so long for them to cool down. There's really no safe place to dispose of them at. So we're still trying to figure that one out. I mean, and obviously there's, the risk of a meltdown when the nuclear reactor just gets too hot and nothing can control it. So we've had some accidents. 3 Mile Island in New Jersey, they kept that contained. Chernobyl, which that's where the nuclear reactor actually exploded, caused a lot of problems. And then Fukushima, where there were 2 reactors that melted down, not because of the earthquake that hit Japan. They made it through the earthquake, but when the tsunami came in, the water flooded everything and the salt water corroded all of the wiring that was keeping the cooling mechanism going. So the cooling mechanism was shut down and none of their backup generators would work. So the power plants got too hot and melted down. And then there's also, the uncontrolled nuclear fission, which is nuclear weapons. We're going to watch these videos together in class, and you're going to see Oppenheimer, one of the scientists who develops the nuclear weapon, talk about his feelings after they tested the first bomb. So yes, the United States is the only place that has ever actually dropped a nuclear weapon on somebody else. We did use it to end World War II in Japan, and it kept the Cold War from escalating into a real war. During the Cold War with Russia, we had multiple targets where everybody had nuclear warheads aimed at different parts all over the United States and all over Russia, but nothing was ever launched. So there were 4 built and 4 originally built, 3 were used, which we're going to watch these videos during class. And really what it is the same type of thing that happens in a nuclear power plant. It's just you don't control it. You just let it keep going. So the nuclear bomb of 1945, known as Fat Man. So this is the one that was not dropped. They dropped 2 in Japan and 1 was tested, and then this is the 4th one. And this is kind of the typical mushroom cloud of an atomic weapon or an atomic bomb. Nuclear fusion, on the other hand, is putting things together. So you're combining 2 small nuclei to form a larger nucleus. There's even larger amounts of energy that are released in this process. So you get more bang for your buck with fusion than you do with fission. But there's no commercially successful plant that exists in the U.S. today. So here's an example of like hydrogen, these 2 isotopes of hydrogen fusing together to form helium and giving off energy in the process. So nuclear fusion is how most of the elements are made in stars. So when 2 or more atomic nuclei combine to form something larger, you're releasing 1,000 times more energy than fission. So that is where, we think of stars as being our fusion or element generators. So here we've got hydrogen fusing into helium, and you get free neutrons being given off and lots of energy. This is the energy producing process taking place in the core of the sun and the stars, and we call it nucleosynthesis because they're synthesizing nuclei. So the nucleus of an atom is actually being synthesized in the stars. The core temperature of the sun is about 15 million degrees Celsius. At these temperatures, hydrogen nuclei will fuse to give helium and energy. And the energy sustains life on Earth via sunlight. So without fusion reactions, life on Earth would not be possible. But the problem is you have to have these super high temperatures for fusion to happen, and we have not figured out how to make that happen successfully in a lab. So a little bit more about nuclear fusion. It would be a superior method for generating power. You get about 10 million times more than a chemical reaction. The products are not radioactive, but the bad part is, in order to achieve it, you've got to have it at several million kelvins, and we haven't quite figured out how to do that. The tokamak apparatus, like the one that's shown up here, uses magnets, uses very strong magnets to try to get fusion to take place. The magnets will heat the material into a plasma state, but we're still not there yet. So we're going to watch this video clip in class, but a little bit about nucleosynthesis. The interstellar medium, so in stars, is about 91% hydrogen and about 9% helium. So all elements start out as hydrogen and helium in a new star, and you just get fusion of the different isotopes of hydrogen, of deuterium and tritium. They fuse into helium and release a bunch of energy. Fusion of hydrogen produces helium, then helium fuses into elements up to oxygen. So in giant stars, we see elements up to oxygen, so up to number 8 being made. Or in a supergiant star, we see up to iron, so up to about element 26 being made. And all the while releasing massive amounts of energy as these elements just keep fusing and fusing and fusing together to form bigger and bigger atoms. When the star uses all that hydrogen, the fusion ends and the star dies. So here's the equation for fusion again. So the deuterium, which is H2, and tritium, which is H3, so just isotopes of hydrogen fusing into helium and giving off lots of energy in the process. A little review of star life cycle. So kind of the average star, which is what our sun is, fusing or making about up to oxygen. We see bigger stars making up to about iron. And then when that star runs out of hydrogen, if it's on the small side, its final destination is going to be a white dwarf. If it's a massive star, it will go through the explosion of a supernova where lots of other elements are made during that process and then end up as a neutron star in a black hole. So this periodic table is really cool because it shows you where all the elements are made. Hydrogen is left over from the Big Bang. Anything in green is going to be made in large stars. Anything in the kind of light blue we find in cosmic waves. Anything in the orange is made in small stars, which is like what our sun is. And then supernova, you can see a lot of these elements are made during the supernova explosion. So all of these elements are found throughout the universe, except for the ones that are man-made. The ones that are synthetic and man-made we don't find. But this gives you an idea about where all of the elements originate from. So we are going to read this article in class, and then we are going to answer these questions as well as watch this video. So you don't have to do anything with this slide right now. We are going to do this in class.